Hey everybody, in this video we're going to talk about predicting solubility and how you do it. In particular, we're going to go through a series of steps. You can see them in these gray boxes that you could use to apply to any potential solute if you're trying to decide if that will be soluble in really any potential solvent. We're going to look at CH2O in water. To be specific, in this video, CH2O is commonly known as formaldehyde, and we're going to try to predict, will this be soluble in water? Why or why not? As we get started, let's first clarify that CH2O is the solute and H2O is the solvent. And I know that based on the way this is written, CH2O in H2O implies that the formaldehyde is potentially dissolving in water. Now that I know what's the solute and what's the solvent, I can start describing them in a number of ways. Let's take a look at the first thing you've got to know. In reference to the solute, which I'll label as CH2O, you have to know what type of particle it is. Is it a polar molecule, non-polar molecule? Is it ionic? Is it a metal? What are you dealing with here? In the case of CH2O, because all of the atoms are non-metals, this is a molecule. And anytime it's a molecule, you further have to decide if it's polar or non-polar. That ends up being particularly important to solubility. And the only way to truly know that is to take that molecule and draw out the Lewis structure to see the shape, how all the atoms and lone pairs are arranged. If you do that for CH2O, it ends up looking like this. I can also see that this molecule has atoms with different electronegativities that are arranged asymmetrically. All of that is to let me officially decide that CH2O is a polar molecule. We're going to skip over here and do essentially the same thing, but now in reference to the solvent. The solvent, remember, we defined as water, H2O. I have to know what water is. Is it a molecule? Is it ionic? Is it a metal? And so forth. Obviously, water is a molecule for the same reason CH2O was. You might also know in advance, just as maybe common knowledge in a chemistry class, that water is also a polar molecule. If you weren't sure, you could of course do the same thing we did before. Draw the Lewis structure and see that there's an asymmetrical arrangement of these atoms that have different electronegativities. Okay, now that I know the types of particles that I'm dealing with in the solute and the solvent, I can describe the types of interactions that are going to be forming based on those types. Well, we're going to jump back and begin with the solute. These are called solute-solute interactions, which just means when you have your, container, beaker, whatever, your sample of CH2O molecules before you mix them with the water. How are those CH2 molecules interacting with each other? What are the attractions? What are the interactions between the CH2 molecules themselves? In the case of CH2O, because the molecules are polar, of course, it's going to have dipole-dipole interactions. Anytime you've got dipole-dipoles, you want to also decide, would those count as hydrogen bonds? These would not count as hydrogen bonds. So that's going to be, I guess you could also mention LDFs, because of course all molecules are going to experience LDFs too, but remember, LDFs are usually not important when the stronger dipole-dipole forces are present. But it's not a bad idea to list them out anyway. We're going to do that same thing for water. If you have just your sample of water molecules, how do those water molecules interact with each other? Of course, water is also a polar molecule, so it is also going to have dipole-dipole interactions between water molecules. These, though, are extra strong and would classify as hydrogen bonds. Of course, we'll add LDFs in there because all substances experience London dispersion forces as well. So our final decision is, what are the solute-solvent interactions? We're looking down here now, almost at the end of the process. What that means is, when you finally mix CH2O with H2O, how are the two different molecules going to start to interact with each other? It's usually a good idea as part of this process to draw them out so you can get a better visual on what's taking place and how the two molecules might interact with each other. So as I do that, we'll represent the potential attractive forces with this orange dashed line. So we're trying to figure out, what is that orange dashed line? We know already that water is polar. We know already that CH2O is polar, so just like any other time two polar molecules get near each other, that's going to be a dipole-dipole interaction. This particular dipole-dipole interaction will count as a hydrogen bond, so we can parenthesize that, and as always we'll throw LDFs in there just for fun. So now I know everything I need to know in order to make a prediction about solubility. The only thing we haven't said yet is how do you actually do that, and what does all this information have to do with that process? For that, we're going to come up to the top of my video screen where I've got a statement written out in green. There's a lot of stuff here, but all we need for this example is that first sentence. Let's read it now. In general, when a solute has similar types of interparticle forces of attraction to the solvent, it will be soluble. What does that mean? My solute has dipole-dipole forces. My solvent has dipole-dipole forces as well. Yes, they count as hydrogen bonds, but that doesn't make a difference. They both have similar types of interparticle forces, and any time that happens, your prediction for solubility will be that solute will indeed dissolve in the solvent. The second sentence following that tells us why that's going to be the case. This allows the solute-solvent attraction, so the ones we labeled in orange, to be strong enough to overcome the solute-solute. So these dipole-dipoles that held the CH2O molecules together, those are going to have to break apart a little bit when it dissolves, and these solute-solvent interactions are going to be strong enough to do that. It's also got to be strong enough to overcome the solvent-solvent interactions. So the hydrogen bonds between waters, those are going to have to break apart a little bit, and these new forces we're forming, the solute-solvents, are going to be strong enough to do that, and that's going to be how you would explain the why behind this. Let's sort of summarize that in some brief language here. So we'll start by saying the hydrogen bonds between CH2O and H2O. Notice we're being specific about which bonds we're talking about. It's these ones in orange, the forces between the solute and the solvent. And then we're going to clarify that we know these are going to be likely strong enough to overcome the solute-solute interactions and the solvent-solvent interactions. And that is how you can predict solubility. That also wraps it up for this video. Thanks a lot for watching.